I made an implementation of Conway's Game of Life that runs entirely on the CPU and it can handle millions of cells. In this video I want to show you how I did this and show you some tricks that I used to optimize this. So the basic idea behind Conway's Game of Life, in case you don't know, is that you have a grid of cells which can either be alive or dead, and then each cell has 8 neighbors, so top, bottom, left, right, and then the diagonals. And if a cell has less than one neighbor, it dies in the next generation. If it has 2 or 3, it stays alive. If it has exactly 3, it becomes alive, and if it has more than 4, it dies from overpopulation. These simple rules give rise to some quite complex behavior. There's a lot of videos of this online. Eventually somebody made Conway's Game of Life inside Conway's Game of Life. It's a whole thing, look into it if you're interested. Most implementations of Conway's Game of Life run all the calculations on the GPU. This is because it can run a lot of them in parallel, and it's also highly optimized to do these kinds of calculations. So the GPU is clearly the better choice. But I was intrigued by a game jam that I found on itch.io, where the challenge was to make an implementation that runs on the CPU and that can still get a lot of performance. So you can do this using the Unity data-oriented technology stack and ECS system. This challenge was hosted by Turbo Makes Games. He has a YouTube channel and he does a lot of videos on this topic, so if you're interested in more details, definitely go check that out. Alright, so I've mentioned ECS a couple of times now, and I want to explain to you what it is. Essentially, it stands for Entity Component System, and it is a different way of working, or a different type of architecture as compared to the traditional object-oriented way that you would use in game engines like Unity. So the idea is a component is just a piece of data. So for example, in the context of Conway's Game of Life, one component can be the position of our cell, for example, and another component is the state of our cell. So is it alive or is it dead? And then an entity just exists to hold components. So for example, we have an entity with 2 components. One of them is a position, and the other one is a Boolean value to indicate whether or not the cell is alive or dead. And an entity with these 2 kinds of components we can think of as a cell in our game. It's important to understand that an entity in and of itself doesn't really do anything, it only exists to hold components. So these components are just structs that you assign a variable, and then you assign those structs or those components to entities. That's how it looks in the actual code. And then systems are nothing more than the code that actually does something with our entities. So it modifies the entities, it runs calculations on them, and then actually runs the logic of your game. So for example, one system that we might have is to calculate the next state of our entities in the next frame, like, are they alive or are they dead? And then to another system might be to actually draw the result to the screen and to a texture that we can actually display. Alright, so now let's head over to Unity and check out how you can use this ECS system to implement Conway's Game of Life. So I have 2 components, one of which is the cell position. So this is just a component with a single variable, an integer 2, which holds 2 integers, so for the x and the y position of our cell. And then a cell alive component, which is a simple Boolean value to tell whether or not the cell is alive or dead. And then we have 3 systems: an initialize system, a run simulation system, and a draw system. So again, systems are just scripts that run to modify entities and their components. So let's have a look at the initialize system. This works sort of similarly like a regular mono behavior. So you have onCreate commands like onCreate functions and onUpdate functions, which run when your game launches and when each frame when you want to update something. So this initialize system simply creates all of our entities at the start of the game. So we want to create a new entity for each cell, and then assign a position component and an alive component to it. Currently I just randomize this alive component to either be true or false 50% of the time, so that when we run the simulation we can actually see something happening, right? The grid is initialized with some random values. So now let's have a look at the system that actually does all the calculations for our game of life simulation. It consists of two jobs. This first one here goes through all of the cells and then takes their alive state, whether or not they are alive, and puts that into a single array. So it essentially just flattens the two-dimensional grid into one array and stores it there. I made this quick drawing to show you how that works. So it's quite simple. You just take all the rows and then put them one after each other, and then you get a one-dimensional array from a two-dimensional grid. Something of note here is this annotation. It essentially tells the compiler that we know what we're doing and we are never going to run into any read-write collisions, because we know that there's only one cell for each position, so there should never be any case where two threads try to write to the same position in the array at the same time. So that's why we can safely do this, and as a consequence we can run all of these in parallel. So that saves us a lot, it gains us a lot of performance. The next job here is what actually calculates the next state of each cell. So it takes this array that we just built, and then it looks for each cell. It looks at their 8 neighbors, and if it has a neighbor, if the neighbor is alive, then it adds one to this neighbor counter. And then these things at the bottom here are simply the actual code implementation of the 4 rules that I explained at the beginning of the video. The rule about if it has 2 or 3 neighbors it stays alive doesn't actually need to be implemented because it doesn't do anything. So these if statements first check whether or not we are out of bounds of the array, because that would cause an error, and then it simply looks at the position of the neighbor, and if this value is true, so if the neighbor is alive, then the neighbor counter gets incremented by 1. Then the last system is a system with a single job. It goes through all of the cells, and if they are alive, it adds a white color to this color native array, and if not, then it adds a black color to it for the corresponding position. This array is then converted to a regular array and passed to a grid drawer script, which simply takes this array, sets it to a texture, and then applies that to a sprite so we can actually see it in our game world. The only other thing I did is I added this simple camera controller script to our camera so we can actually move around and zoom in and out. But if we now run our game here, you can see that it is working. So I initialized this to 1000 by 1000 pixels, and it is already running relatively smoothly, but there are still quite a few things we can do to improve this. If we have a look over here at the profiler, which maps how long all of the different frames take and what is taking up a lot of time, we can see that the jobs over here, which is the main jobs that we are running, that I just explained, aren't actually the bulk of the time that is taken up by each frame. I looked into this, and the thing that actually takes up the most performance is simply drawing this texture, so that's something that can definitely be improved. Before moving on, I want to quickly mention why this is so fast. What are the real advantages of this? So first of all, ECS makes it really easy to implement things that can run in parallel, because you're simply modifying data, and if you do it right, you can make jobs that can run, they can do this in parallel. And also because all of these components and entities and stuff like that are just simply saved in memories in large arrays of values. This makes it really easy to do some very low-level optimizations, and you can take advantage of this by adding this burst compile attribute. So what this will do is it will actually compile this code into some very low-level, highly optimized machine code that can run a lot quicker than if you were to do this without this burst compile attribute. So that's why this has such an advantage over just regular object-oriented programming. The first improvement I made was just adding some features. So I can now dynamically change the grid dimensions. So if I want 1000 by 1000, there you go. And I'm using Graphy over here to actually show what my current frames per second is. So in this first implementation here, 1 million cells can be rendered at about 30 or 35 frames per second on average. The first improvement we will try to make is to the rendering of our image. So instead of using, like we did before, the set pixels and then passing an array of colors, we'll use this load raw texture data method, that will take in a native array. This is much quicker because it essentially just tells the texture to look at a particular place in memory for an array of, in this case, bytes that will hold the actual color of our image. Now I say color, but we are actually using this alpha 8 texture format. So this is a texture that only holds alpha values, which are transparency values. We do this because otherwise, if we would use regular color, we would have to use 4 values, so for the red, green, blue, and then the alpha channel, whereas here we only change the alpha channel. And what we then do is we actually place another texture behind our image that is white. So if we want to display white, we just set the transparency to be fully transparent, and then the texture behind that will be rendered. So by doing this, we can get away with using a smaller array to actually represent our image. And then in the draw system over here, instead of assigning colors, we just assign a byte value. So this is a transparent value and this is a black value. And with that change, if we now look at the new performance of our simulation, we can see a very dramatic increase from about 30 frames per second to more than 200. So this was definitely a change worth making. The next improvement we can make is to our cell position component. So right now we are saving this position as an int2, so one x value and one y value. But then in the run simulation system, we have to calculate a one-dimensional position of our cell for the set alive array, and also for the calculate next generation. We have to do it each time. So why don't we just save the one-dimensional position directly, and then we don't have to do all of these calculations. So now the position is a simple 32-bit integer, and we can simply look up our position cell by passing the position directly, not having to calculate anything. And same over here, the calculations are much simpler. And if we now go back to Unity, we run this, let's see if we got any performance improvements. So here again, we went from 200 frames per second to about 300, so quite a significant increase there. The next improvement I want to make is to this whole mess of if statements. I think this can be done a lot better. So there you go, now it looks a lot cleaner. I got rid of all the if statements that check if the neighbor is outside of the array, because what I did instead is I simply made the array like 2 bigger, so that there's an edge around it of all false values. So now we don't actually have to check if we are outside the bounds of the array, because the array will still be there, it will just simply be false, so that saves a lot of if statements. And also this top value over here needs to be calculated 3 times, so instead of doing it 3 times, I simply calculate it once over here and then pass that to the 3 if statements, and the same for bottom over here. So let's see what we got in terms of performance improvements again. So for 1000 by 1000 we are now up to 330 frames. This has a very small impact on performance, but you know, still it's something. The next thing I notice is that in run simulation system we calculate an array to set all of our alive cells, and then in the draw system we basically do the same thing, right? We calculate an array again to set all of our alive cells to some particular value, so you're essentially doing the same work twice, and this can be improved. So now in our run simulation system, instead of calculating an array of booleans to determine you know, if the cell is alive or not, we'll calculate an array of bytes with 0 representing if the cell is alive, and 1, 1, 1, 1, 1, 8 ones, and representing that the cell is dead. And then we simply check, instead of directly checking for a boolean value, we compare it to check if it's equal to 0, and then that would mean that the cell is alive. So now we actually already have an array of the correct values that we need, so we directly pass it to our apply texture function over here, to the grid drawer. And we actually got rid of the draw system entirely, so that whole chunk is gone. We don't need it anymore. And now if we try to run it again, let's see if we got any significant improvements. And there you go, another, let's say 30 frames per second, so not as significant as the first changes, but definitely worth it. So in the end we ended up with an implementation that can run 25 million cells at a quite comfortable 30 frames per second, but as you might be able to hear, my CPU is suffering quite a bit from this. But yeah, it was fun, interesting to learn about. If you have any ideas how this can be improved further, definitely let me know. I'll leave a link in the description to a GitHub page where you can download this project. Other than that, all that's left to say is thank you for watching.